Can you guys hear me? Rahman, can you hear me, Rahman?
Yes, doctor.
Okay, right,
Now
good. Thank you. Right, so I have to ask because I normally in front of my desktop while doing this lecture, but because my son is having a small party with his friends, not really a party, food party, party game party. So I need to move elsewhere to do this lecture. Since it's already 5:30, I will just make a start because if you notice that the lecture notes are actually quite long. There's about 60 something plus lecture notes slides. So therefore, I'm thinking of just starting early, even if we have not yet, not everybody's here yet. I know one of your friends, Tamila Rasi. She is a nurse in Perak. This is just to inform everybody. She told me that she cannot attend to this class, and she even asked for an extension for her assignment submission because she is actually working for us. So she's a nurse, and as you guys know, the COVID-19 pandemic. Yesterday's case we have about 4,000 something. So she's one of the frontliner that is actually helping to help these people. So I give her a thumbs up. I give her a go so she can actually skip this class for today. And she can extend and submit her assignment next week. All right, so I will just make a start. So today we have two sub topics. So first one is method development and second one is troubleshooting. I'm hoping that I can finish it within 2.5 hours because we will have about half an hour break at about 7:30 p.m. And if you can't hear me or somehow I'm lagging or whatever, do let me know via WhatsApp because again I cannot because I'm presenting through my iPad, so I cannot see whether my connection is off or if there's something wrong, something bad actually happening. Okay. All right. So first off, we will look at method development, and this slide or this section is a bit short. It's not that long. And then we'll look at troubleshooting because there's more issue on running an HPLC. Okay, and so I think we'll just make a start. All right, so this is today's attendance. It is the same link as what you guys used last week. So if you actually missed it, then you can just review the pre-recorded lecture and just scan this QR code and submit your attendance. Or alternatively, you can just quickly do that or use your phone or whatever. Or otherwise, once the lecture has finished, I will put up this recording on Spectrum and you can view it again. Okay, so today is our last lecture. So instead of having a full 7 weeks of lecture, so as I mentioned previously, on week 10 and on week 11, we actually had a Christmas break and a New Year break. And then on week 12, we had summative assessment and a quiz. On top of that, on week 8, half of it was used by Dr. Mugunda. I'm not sure what he did for. I think he kind of like finishing up all his lectures, if I'm not mistaken. Okay, so but basically we have gone through all of these, even though it's not in very detail, and we were not able to do a lot of tutorials and practices in the class due to time constraint. But I'm hoping that today we'll be able to finish these two subtopics. Okay, so I'll be always watching my time so that we are on track and that you don't have to spend extra time to watch this lecture again, or All right, so let's move on. Lecture number 4, method development. Okay, so one thing that you need to know is that even without listening to this lecture, you should be able to understand everything quite clearly, because I'm not sure if I can actually finish all the explanation in time. So what I did for this lecture is actually to write down everything that I can say. Okay, so that's why if you compare this lecture to the previous week's lectures, this time around there's a lot of words. Okay, everything is filled with words and images, figures. So like, for example, this one, instead of just putting in approaches for initial method, I actually write down this lecture provides an overview of modern HPLC method development and discuss the approaches for initial method development, particular focus on column, detector, mobile phase selection, method optimization to improve resolution, and emerging method development trends. So I actually kind of like write down what I want to say instead of just putting in all the keywords. So this lecture will be very wordy. I'm hoping that everybody, it doesn't matter if you want to stay, or if you have some other things that you need to do, you can leave by all means, because this lecture is very straightforward. And there's not much really explanation to do because I've already written it down. Okay. Again, as I previously mentioned multiple times, the focus of the HPLC lecture is mainly on the reverse phase method. Okay, because again, RP, or reverse phase HPLC, accounts for about 60 to 80% of at least the application in Malaysia. I cannot generally say everywhere in the world, but normally the reverse phase HPLC is the main method of choice, because you can use this method. You can just simply change your column. You can set your equipment as RP HPLC. You can just change the column to suit to whatever you want. Okay, so that's why the usage is actually quite huge compared to the normal phase. And anyhow, a normal phase, there are a lot of other instruments that can actually do that. Like, for example, the open column using silica gel. Okay, we have flash chromatography. So those kind of other types of instrument that can actually cater for the normal phase. So HPLC is normally, nowadays at least, normally used for reverse phase applications. Right, so developing and validating new analytical equipment is normally costly and time consuming, especially if, say, you are thinking of opening an analysis company, or if you are working in an analysis company, then definitely you,
Hello, doctor.
yes,
Are you projecting the slide? Because I can't see the slide.
can everyone else see the slide, or
No, no.
Cannot see,
no?
doctor.
Okay, I'll just redo it. Where did you stop, or did you can't see it from the start, or what? Anyone? Can you see the slide now?
From the start.
From the start, okay. That is very funny. So you didn't see this, the attendance?
Yes. Yes.
Oh
Yes.
God. All right. So I was
Okay.
talking to myself on my own. But anyway, the first few slides are not important. You can just quickly do your QR for the attendance. Because I was saying, if you can't see my slide, let me know and whatnot. And it's already been like a few slides, so I thought everything is okay. Sorry about that. All right, so tentative schedule, you probably just listen whatever I said. This one is not really critical. It's just saying that what this lecture covers, and the primary thing that you need to focus on is the focus of this lecture, and the example used in this lecture is a reverse phase HPLC. Okay, so I was saying about this, which is developing and validating new analytical method is normally costly and time consuming. So if, say, you are working in an analysis company, or you just started working in an analysis company, and that company asks you to develop new methods for, say, analysis of an oil water sample, for example. Okay, so depending on what you want to analyze, there might be a lot of time consumed to actually develop a method that you can utilize every day. Because normally, if you are working in an analysis company, the analysis bit is kind of like a repetition. So you might do it daily, or you might do it monthly, or you might do it yearly. But what you need to do first is to know what method is suitable for the goal that you are achieving. Okay, so if you are analyzing a metal uh, a metal source in say a river compared to a household, so if the metal of interest in these two places are similar, for example, I was saying one is household and one is from a river. Okay, so if these two places, the metal that you want to analyze is similar, for example, mercury. So you want to make sure that the method that you develop can be used in all household and in most types of rivers. Okay, you as best as you can, you don't want to recreate a new method for every single house. Okay, so because of the time consumed to develop the method itself, so if you were to create one method per house, then it will, if you have 1,000 client, then you need 1,000 method, which is time consuming. And of course, to develop methods, you need to use a lot of solvents, and therefore it will come under a high cost. So what you normally want to do is you want to create a method that is kind of like general, that can be used for the purpose that you want. So if you want to analyze water sample in houses, then you might want to develop a method that can cater to all houses. Okay, doesn't mean that 100%. It might be in 60 or 50% of all houses, and then the other 40% you are using second methods and whatnot. But the idea here is you want to develop a new method is costly and therefore time consuming. Well, it's time consuming, therefore it's costly. Okay, and throughout literature says, so what you need to do is normally to minimize the time that you need to spend to create a method from scratch. What you might want to do is first do a thorough research, literature research, using based on existing information that you can get from websites, from in Malaysia, probably from our environmental ministry, or you can use sources from overseas, from different countries, especially if the method that you want to develop is not available in Malaysia, or uh, it's not a main focus in Malaysia. So you might want to find different sources from the internet to search for similar goal, but it doesn't have to be 100% exact. Okay, because towards the end of the day, what you need to do is you want to develop a method. If you can get the method from elsewhere, you still need to validate the method to make sure that the method that you are using is actually valid to the purpose or the current situation in Malaysia. Okay, this should include a computerized search of chemical abstract and other relevant sources such as monograph, for example, using USP or EP, journal articles, manufacturer literature, and in general, internet or Mr. Google. Okay. So what is the general strategy? So by no means that this strategy that I'm presenting is the only strategy available. So these are the general ones, meaning that if you don't know anything, you can start off with this. But if you do know something, then you can either skip, or you can either introduce a different strategy to actually develop your own method. So this is the strategy to develop method. And All right, so first one is you need to define the method, and you need to define what is your goal. Okay, we will go through these 5 steps in a bit detail, one by one. But in general, you need to first you define your goal, define the method that you want to use, and you need to know what is your separation goal. What samples you are trying to separate, what samples you are trying to focus on, and then you need to gather the sample and analyze information. Why? Because once you know what samples you are planning to measure, and based on the sample, you know what analyte you want to use. So if your sample is best used for a normal phase HPLC, then your analyte must be compatible with the normal phase HPLC. Likewise, if your sample can be used for a reverse phase or for ion exchange chromatography, the analyte must be compatible to the type of sample that you want to analyze. That's one thing. Okay, the analyte. Second one is column. I didn't mention anything about here column, but column comes under here. So once you know the sample, once you know your analyte, therefore you can decide on what column you can use, or what column you need to use to ensure that your analysis can run smoothly and can be a valid method. After which comes the initial method development. So this is normally a scouting phase, whereby you've already know your sample, you've already know the analytes that you want to use, you already know the methods that you want to use, and you know what column you want to use. So once you have everything ready, not just randomly picking this and that, but knowing based on the information that you have, then you go into the initial method development, which is just scouting, meaning that you just run it once and see how it goes. If everything is okay, the chromatogram that shows you a good separation, then you move into fine tuning and optimization, meaning that maybe in your analysis you have 2 peaks which are close together. So from here you can do fine tuning. You can play around with different column. As you remember, once you have a longer column, you get a better separation. So you can play around with combining columns, or changing the concentration, the gradient concentration, changing methods from a gradient into isocratic flow, and some other stuff. Temperature, you can play with pH and whatnot. So there's a lot of optimization and fine tuning that you can do to achieve your goal, which is to separate, in this example, which is to separate the 2 peaks which are very close to one another. Okay, so once you have completed your optimization, okay, so say for example, now the 2 peaks can now be separated into 2 equal good separation and whatnot. What you normally do next is you validate the method. So method validation here means that you might want to repeat the whole process in a different day. So in a research field, normally what we do is that you validate the method in 3 different days. Okay, say for example, if I have developed one method to analyze water samples from households. On day one, say for example, I achieve this type of peak. And then day two, I want to rerun the same method, and I want to make sure that I do achieve the same peak. And similarly on day three, same thing happens. Once you achieve this, then you can confidently say that my method works, and now the next phase is to find clients. Okay, so that from the client you can generate your income for the company. This is generally the strategy to develop method for HPLC. So let's go in a bit of detail for each step. So step number 1, define the method and separation goal. So what does it mean? So defining methods means that you need to understand whether the aim is to do a qualitative method or a quantitative method. So are you just analyzing whether say for example mercury is present or absent, or are you actually measuring say for example a copper content? So copper is not really it's toxic above a certain level, but at a very low concentration it is considered as rather safe. So if you were to do a qualitative method, you just want to confirm whether it's normally on something which is very critical in the presence or absence of that particular metal or whatever. Okay, whatever sample that you are measuring. So that's why um, if you are to measure mercury in household water, for example, then you might want to focus more on qualitative method, because even in a small quantity of mercury, it is still dangerous. So you just want to confirm if mercury present. If yes, then you can straight away say this water source or whatever is not safe. But if you are thinking of measuring copper, the presence of copper is very, very likely, because old houses especially, which are using copper for a lot of things, electrical wiring, some might use copper for water heater system. So you definitely will see a little bit a presence of copper. So if you are thinking of measuring copper, then you need to know the quantity of copper present in that water source, so that you can definitely say whether this water source is safe or not. Okay, so in this case, qualitative method, UV spectra data from photodiode array detector or PDA are often used as a secondary confirmation technique. This type of method can be a limit test to evaluate whether the level of analyte is above or below a certain present limit, or to generate a chromatographic profile of comparative purposes. As I mentioned, if for example, if you are looking at measuring the presence or absence of mercury. In contrast, for a qualitative method, it generates information on the concentration or the amount of analyte in the sample. The example that I gave you just now was copper. And system calibration or standardization is typically used using external standards or internal standards before you actually measure the water source. A quantitative method is more difficult to develop and requires extensive effort for validation. Okay, this is because, as I mentioned just now, in very general, when you do your validation, normally in my case, I will do in 3 different days. So imagine if you are doing a quantitative experiment whereby you need to do a system calibration, therefore your calibration needs to be done in 3 different days. Okay, if you are doing some research about a quantitative method analysis, some journals requires that the data are not from 3 consecutive days. Sometimes they require like 3 data points, 3 data plots from 3 different days, but the days must be like differ in a few days, like for example day 1, day 5, and then day 10 or something like that. Okay, so that's why I write down that quantitative method is more difficult. It doesn't mean that it's impossible, but it's just more difficult. Analytical method goals are often defined. Okay, so now we are talking about the goals. Defined as method acceptance criteria for peak resolution, precision, specificity, and sensitivity. For example, if you are working in a pharmaceutical method, for potency assay of an active compound or API, it typically requires the following. You need to have a resolution which is bigger than 1.5 AMU with the So this one not just MU. This one is I think about minutes. Okay, resolution to peak separation, larger than 1.5 minute, I guess, from the closest eluting components. Precision of retention time and peak area, which is less than 1 to 2% RSD, and linearity of the range of 50 to 100%. All right, so this is an example for pharmaceutical analysis. But this one is the same. I should have put that one a bit to the front. And analysis time, you don't want it to be very short, and at the same time, you don't want it to be very long. Because shorter runs, sometimes you won't get a good separation, but longer runs, even though you can get a good separation, but now it becomes costly. Okay, and you also want to have a minimal sample workout, because if you do a multiple or a very tedious sample workout, then you need to spend a lot of time to actually prepare your sample. And imagine if you are doing a repetitive work daily, and every day you need to keep on preparing your sample again and again. So it will be very tedious, time consuming, and therefore costly. All right, and you want a robust method that does not require extensive training for execution, meaning that if you were to train someone else, it would be very easy to do, or very flexible. And finally, you want the low cost per analysis, therefore low reagent. It doesn't really affect the instrument too much, or the electricity that is being consumed is low. For example, for Hplc, you do have an oven component, so as best as possible, you want to avoid using the oven at high temperature, because not just it can what do you call it, reduce the half-life of the column, but it can also for a long run you will need to pay a lot more for electricity.
Doctor, can I ask question?
Yes.
The linearity 50 to 150, just to understand, what is it means here, 50 to 150?
Okay. So linearity means that when you want to run your sample, you want it to be, say, at for a different concentration, you want it to be what's the word, it doesn't jump too much. Okay, so you want your method to be as sensitive as possible, so that if you do it multiple times, there are correlation, that's the word, there are correlations between the sample that you want to analyze. So there must be a linear um, correlation between the sample that you want to run, and normally you want it to be 50 to 150 in terms of concentration, so that for pharmaceutical drugs, for example, there's normally a range whereby if the range is too low, then either the drug will not be efficient, or it will be degraded too much, that when you run it, the sample will be so small. And at the same time, if the concentration is too high, because this is just focusing on pharmaceutical, okay, so but if the concentration is too high, the person might actually be dead altogether, so there's no point of analyzing it. So you want it to be what's the word again, correlates. You want the concentration to be in correlation between one another at different concentration using the same method. Is it clear?
Okay, I just wondering 150%, it means it's over 100%. Just wondering, any special reason for pharmaceutical methods that can up to 150%?
150. So this is a comparison. Say for example, if your method is very sensitive, okay, if your method is very good and your HPLC system is very sensitive, of course you want it to be able to measure something which is so and oops. So this is not just about detector, okay? Of course, there is a correlation with the detector. And the easiest example is the UV vis. Remember a long time ago, UV vis, the detection limit is about 2. Okay, nowadays, as the equipment advances and the laser technology and everything advances, the upper limit now becomes 6. Okay, so using the same sample, oh, I keep on changing the slide. Using the same sample, now you can measure up to a higher degree of correlation. So what it means here is that you want your method, if say you change a detector, just solely changing the detector because the detector is old, you want your method to be able to get a higher range of detection, not just simply stop at 100, but a higher range, because sometimes you do need to do an extrapolation or interpolation. So those kind of things comes into play. So that's why the range is very big. It's like 50 to 150 percent. Okay. And this is a number that is not fixed. So depending on equipment that you use, depending on the column, if you are using UHPLC, which is a better equipment than just generally HPLC, the number might go lower between 20 to perhaps 200%. Okay.
So, doctor, so the percentage is referred to the concentration of the analyte in percentage or refer to a recovery of the linearity? Because I thought if it's think of a concentration, then I don't get it on 150 because concentration is only up to 100%. But if you're talking about recovery minus plus, then probably that makes sense on that.
It's not recovery because
recovery.
for pharmaceutical analysis, for
Mm.
pharmaceutical API, so
Mm.
the focus here is for analysis.
So
So
it's this percentage is concentration.
yes, it reflects on the concentration, but it doesn't mean that the concentration is 100%. It means that, say for example, today the sample that you are analyzing is 10 ppm. So next week or next month, the sample that you get from a different source might be what did I say just now? 10 ppm. Okay, so the week after it might be 100 ppm. Now you have an increase of 100-fold increase in concentration. Okay, so those are the things. That is what
Oh,
I mean.
okay.
Yeah.
Okay.
So it's
Okay.
concentration, but
All
it's
right.
in a percentage form.
Okay. All right. I get it.
All right.
Okay. Thanks.
All right. So gathering sample and analyte information. So this is the second step. So you need to know the sample and analyte information. This information is useful for selection of appropriate sample preparation procedure, as well as initial detection and chromatographic modes. So this is, as I mentioned in the first strategy slide. Okay, the chemical structure of the analyte furnishes data on molecular weight and the nature of the functional group. So again, if you have a more polar sample, you can either choose to use RP-HPLC with a compatible column, or you can choose for a normal mode HPLC. Or otherwise, if your sample is more hydrophobic, then you might straight away choose a reverse phase HPLC. But again, depending on the polarity of your sample, you can choose either C18 or C8 or even C4 column. Okay, so this is what it means by molecular weight and the nature of the functional groups. So particular attention should be directed to acidic, basic, aromatic, reactive functional groups from which the estimate of pKa, solubility, chromophoric stability data and there's a lot more. So it's quite difficult to list down everything, but basically knowing the molecule is very important. Okay. MSDS should be gathered if available to develop appropriate guideline on safety handling procedures. All right, so not just knowing the sample molecular structure, but you need to know whether your molecule is hazardous or not. I know because most of you guys are chemists. So if you see C and N with a triple bond, then you definitely know it's a cyanide and it's dangerous. But for those who are actually not from a chemistry background and probably not on a biological background, they might not know this. So consulting MSDS to ensure that you know what are the appropriate safety measure to run your sample, or what you need to do after you run your sample, then is very critical. Okay. Additionally, not to forget, information regarding sample preparation procedure are critical for pre-HPLC run. For example, if you have a solid handling, okay, so if say you have a solid sample, so therefore the type is solid handling, you need to know what are the procedures involved in preparing the sample before you can run into HPLC. Because again, HPLC, the requirement, one of the main requirement is for your analyte to be able to dissolve in your solvent. Okay, so if the original sample is in a solid form, you need to know what are the procedures that can be done to make sure that the analyte that you want to measure is soluble in one of the solvent. Okay, so one operation that you can do is first grinding, of course, to break it into smaller pieces, or milling or homogenization. And then after which, say for example, if you are measuring a metal content from soil. Okay, so soil is a very hard solid. So first off, you might want to wash it and whatnot, and then you found say 0.1 millimeter of a metal-like substance. So you might want to grind it, you might to mill it first, or you might want to do an acid analysis, or not acid analysis, acid digestion on the solid, so that you know that you are forming an ionic form of a metal, and for sure it will dissolve in the solvent that you want to use for your HPLC. Otherwise, if you don't know about this, if you don't know about your sample type, and you did not do the procedures that you need to do before your HPLC runs, it's and you straight away move to running your sample. So the first thing that you will do is, if your HPLC machine has an automatic injector, it will definitely block the injector. If it's small enough that it can pass through the injector, it will then block the metal freight inside the HPLC. Okay, there's a lot more. There's a lot of places where there's actually like a very small metal freight. I think I covered it a little bit in lecture number 8, I think, or probably it was last year. I can't remember, because last time I actually brought the students to the lab and show you a little bit about HPLC and where are the location of the metal freight that I'm talking about. Okay, additionally, by knowing the sample, you can know what are the extraction method that you might want to utilize to extract out your sample or your analyte of interest. Okay, so and so on and so forth. So this is basically very general. You can just read through, and I think it's basically the idea is similar. By knowing the type of sample that you want to analyze, there is an appropriate operation or pre-procedures that you can do or you must do before you actually inject your sample into HPLC for your run. Okay. Similarly, once you have processed all this, you can find the compatible analyte. that can, not analyte actually. Analyte information is the same as sample. Solvent. You can find the solvent information that is appropriate for the run. So initial HPLC method development. So this is the third step for the strategy that I mentioned. Okay, so during initial method development, a set of initial conditions, for example, mobile phase, type of column, type of detector, is selected to obtain the first scouting chromatogram of the sample. So basically, this one is just a general run that you want to see how the spectra look like. So in most cases, again, based on reverse phase separation on CAT column, what we normally use is a UV-vis detector. Or at least in my case, because I'm doing a peptide analysis, so my work normally involved in peptide analysis. So I can simply use UV detector to detect the presence or absence and the quantity of my peptide. Okay, a decision on developing either an isocratic or a gradient flow should be made at this point. So if say your sample is from is a synthetic sample, okay, so synthetic versus natural, I will say, for example, from a river. Okay, synthetic is of course you synthesize it from the lab. So once you synthesize something in the lab, you cannot guarantee that the reaction that you are doing is 100% in the completion without any byproduct. So in this case, you might want to use just an isocratic flow, because you know that if you do A plus B, you cannot get more than 4 different compounds unless if you actually or accidentally synthesize a polymer. Okay, just imagine that A plus B is not a polymer compound, so you can either get AB, AA, BB, or BA. Okay, so these are some of the possible construct that you can get. Of course, you can get polymerization, you can get different types of AA, but this is just the general form. So if say, for example, in theoretical, you know that A plus B can get 4 types of compound, which are not that much, okay? And you know that, say, for example, A and B elutes at between 20 to 30% of your mobile phase. Okay, so you will definitely elute at between 20 to 30%. So instead of doing a gradient run, which is normally taking more time, so you might want to just straight away run an isocratic flow at 20 to 30%, or either say start off with 20% and then you move up bit by bit. All right, so and in contrast, if your sample is from nature, whereby it might contain a lot more dissolved analyte, it might be analyte of interest, it might not be analyte of interest, but you know that from that source, normally you will have multiple samples or thousands of samples. So you might want to start off with a gradient flow, whereby you start off with 0% to 100% of your solvent concentration, so that you can generally see what are the spectrum, how will the spectrum look like. Okay, by doing this, by doing your initial method, after this, then you can proceed with fine-tuning and optimization, especially say, for example, if your spectrum is like that, okay, and this one is, for example, 0 and that one is 100%. Just ignore the x-axis. Normally x-axis is minutes. This is just an example. Okay, for example, if that is your gradient, 0 to 100%, but then the compound or the analyte that you want to analyze, that you want to look at, is at 50%. So by knowing this, what you can do then is you can develop a method that can fine tune at 50% concentration, so that you can get as best purity and uh, at the higher resolution, at the higher, basically the best. Okay, so the scouting method, the scouting step is just to look at how the spectrum will look like depending on your sample. Okay, additionally, if say you have a few detectors in your company or in your lab, then that you know that this detector can serve a certain advantage to the sample or the analyte that you want to measure, then you might want to change it. Okay, so you might want to check, probably for your first scout run, you use UV-Vis, and your second run, you use ELSD, your third run, you use MSMS, and so on and so forth. So each of these detectors has their own pro and cons. There are its own advantage and disadvantage. As per your assignment, you work with one detector, you know what are the best, what is the best sample for your particular detector, and you know that there are some disadvantage of your own detector. I'm hoping that you actually include that as part of your writing, not just all the positive thing. Okay, there's a mark for that comparison, but anyhow, so some example of mode and detector selection is on the next slide. Okay, so say for example you have two different type of sample. One, you have macromolecules with a molecular weight larger than 2000, while the other one is more an organic molecule which has a molecular weight less than 2000. So the analytes that you want to measure can come from an organic polymer, or it can be a biomolecule from cells, for example. Okay, by knowing this, you know your sample type, you know what are the analyte type, you can choose your own method to run the HPLC. Okay, so this method, it can be either a reverse phase or ion pair, ion exchange, a helix type, HIC, NP, gel, and so on and so forth. So by knowing your sample from the second step, and then you move into the first initial HPLC method development, whereby you just randomly run, you can actually know, or you can actually see whether the method that you selected first is actually suitable for what you want. If it's not, then you do it again. You do a scouting phase again and again, again and again, until you finally kind of like satisfied with the initial method. Okay, meaning that this is the method that I want to use, this is the detector that I want to use, this is the process that I need to do before I run the sample in HPLC. Once everything is a tick, a good, a go, then you proceed with fine tuning. Okay, another example on initial method development. So one of the things, if you are using UV-Vis, regardless of what detector, of course, UV-Vis is the most common one. So that's why I'm using UV-Vis detector as an example here. Okay, so you need to know first is whether your compound is a chromophore. If it's a chromophore, then you will absorb light at a certain wavelength. In this case, it's an example of a sample which has a minimum of a double bond, because the wavelength shown here is between 200 to 400. So it's normally a double bond. Either it's benzene or non-benzene, and so on and so forth. Okay, now once you know that the compound of interest has a chromophore, you want to start looking at this particular region. That's one thing. And then once you know the general spectra of your compound, because when you do analysis, normally you already know how the analyte of interest will look like. Okay, that's the general thing. So say for example, as I mentioned, if you want to measure a mercury in the water, then definitely you will have a mercury sample somewhere in your a mercury standard. That's the word. So you need to have a standard. So you definitely will have a standard in your run, because without standards you cannot know which is the analyte of interest. Okay. In this case, so once you know your standards, you will have your sample. Okay, you have your standard, and then you have your sample. And then your sample can come from many different resources, which might contain more than one sample, which normally, of course, it contains one or two or more analytes. So, and one of the analyte is your standard. So what you do next is, if you do know the other analytes, what you want to do is, normally you want to look at the wavelength of each component, if you can. If you can't, then it's fine. You can still skip it. But as part of a method development, normally you want to look at individual. What are the other competitive a competition that might occur in your run or during your run. So if say you have your standard is like that, so of course you want to use a 241.5 nanometer as your um, as your wavelength of interest. Okay, if say for example you have something like this, whereby you have 3 lambda max, you might want to choose one of them. But if you have both of the sample in one in one sample, if you have these two compounds in one similar sample, okay, A and B, for example, so which wavelength is best suitable if you want to measure just sample B? Okay, of course, in this case, if you answer 214, you are wrong, because the best choice is 338.7. If you were to only measure analyte B, because at this particular wavelength, nothing is present on analyte A. Okay, so there are some plays in there. So in your initial method development, you might want to run different wavelength. If you have a PDA system, then it's fine. You can just run all wavelengths simultaneously. But in case if you don't have one, then you need to play around by changing the wavelength of your detector so that it can measure, it will have the highest sensitivity to the analyte of interest. Okay, generating first chromatogram and fine tuning. So this one is step number 4. It's more on fine tuning. So in a case study whereby the method goal is to develop an MS compatible composite method, is a combination of assay and impurity for a drug substance. This pharmaceutical, the API is basic salt with pKa of 8, good solubility in water, especially under acidic condition and UV spectrum, as shown in this picture on the right. Okay, how do you proceed? Do you proceed with isochromatic, or do you proceed with a gradient? So step 1, if you were to proceed with isochromatic illusion, you start off with injecting the sample in a mobile phase at low concentration of ACN. So this is similar to as I mentioned previously, whereby if say you know that your sample will elute at about 20 to 30%, and if you're thinking of using an isochromatic elution method, you just pick randomly, or not really random, of course, because you know the values already. So you just choose one concentration and just run it. And then while running it, say for example over here, you can see at 35% ACN, the sample elution 1 is very quick. Okay, it's too quick that you cannot actually see the injection peak. Okay, if you see here, so the initial bit of HPLC is normally when you see kind of like an injection peak. I like to call it as injection peak because when you inject your sample, depending on the gradient um, of the HPLC itself, so you can prepare your sample in a different solvent than the solvent that you want to use to run your HPLC. So this is the solvent peak that you will see if that is actually what you did. So say for example, if you prepare your sample in methanol, but then your HPLC run is in acetonitrile, you will see a peak like this emerging. Okay, even if you inject, if you prepare in methanol and then your system runs in methanol, you will definitely see it. It's either the peak is small or it's big. Okay, so you want the peak to be very visible. And something like this at 35% acetonitrile, whereby the injection peak and the peak of interest is very close to one another, you cannot really use this spectra to quantify the amount of analyte in the spectrum. Okay, because that peak contains a negative peak and a positive peak, so you might not know whether there might be a negative underneath or overlapping peak with the peak of interest. So this is a bad example for an isocratic flow. So because you know that at 35% ACN, say for example, if this is the first one that you run, because you know at 35% ACN, your analyte elutes very, very quickly, you then go down into, you go down to about 30% acetonitrile and see how the spectra changes. And then you keep on going again at 25%, or if you have a lot of time, you might want to go 29, 28, 27, but normally you just skip through either 10% or 5%. That's normally what people do. So you go down to 25% ACN, you get a peak, something like that, and then you go down again to 20%, but then you see a peak tailing out. So you know that the limitation is 20%, because at 20%, once you see a tailing peak, it's either your sample now elutes very, very slowly, or there's some issue. If there will be issue when you go lower than 20%. So now your limit is between, I would say 30% to 20%. So by doing this, you will get like, well, 25% might be the best for this initial run. So you start off with 25 and then you further optimize it. Okay, so that's how you do it if you do an isocratic illusion. Okay, so you choose the best chromatogram that gives the best resolution, symmetry, and balance with time. You don't want to have, say for example, for this one, other than the peak tailing, if you look at the time comparing to 25% ACN, now the time increase is more than 10 minutes. So if you were to use 20% ACN, you know that you will use a lot of solvent and you are basically wasting a lot of time. So your first 10 minutes is basically nothing. But if say something is coming out here that is of your interest, then of course it is fine. But for a sample like this, whereby there's only one analyte that you want to measure, then 20% is of course not a good option. So you either choose 30% or 25%, or choose a value in between 30 to 20 that gives you the best results. So best to use additional detector or method to validate your purity of the sample if you were to use isocratic. Okay. In contrast, if you are doing a gradient illusion, what we normally do, or at least what I normally do, is I will start off at a low concentration of ACN and definitely go to the highest percentage of ACN that is possible. Okay, so that what it means by broad gradient. Initially, for my setup, because I know peptides dissolve in water a little bit, but it dissolves in acetonitrile at a greater percentage. So I normally start off my run at 10% and finish up at 100% acetonitrile. So this is what I know. So this is my normal protocol for my first scouting method. Okay, so once I know where the peak comes out, for example, if you look at this image on the left, the API eluting at about between 35 to 40% ACN. Okay, what you want to do next is you might want to run, or during your optimization process, you might want to focus on between 30 to 50% ACN, because this is the concentration by which you know that your compound will definitely elute. Okay, because if you keep on, still using this method, not only that you are wasting a lot of time, you are also wasting a lot of solvent, because you know that above that one is about, oh, I do have the gradient. So that one is 5%, that one is about 95%, so midpoint is here. So that one is probably about 60%. So at about 60% acetonitrile, you know that nothing is coming out. Okay, so you can see down here, it's very clean, it's very clear. So meaning that your sample does not contain impurities that will elute out above 60% ECN. So to develop a method, you might want to, if you still want to start at 5% ECN, you can start at 5%, and at 60%, you can quickly stop the run, and that's it. So now you will save about 8 minutes. Okay, so that's why running a scouting method, or just a scout run, is actually very, very beneficial, because you can save a lot of time, and also you can save a lot of solvent. All right, so what is this all about? Step 1 for gradient elution. This one should be step 2, but PDA collected between 210 to 400 nanometers. During your scouting phase, the chromatogram on the left was observed. What wavelength should you choose? Okay, so now you have a wavelength like this between 200 to 400, and you see there's two kind of like peak of interest. Okay, so one is this, that's one of the lambda max, even though the absorption is not very good, or additionally you have an absorption which is very good at 200. So which one should you choose? I think the answer is already there. So you want to choose a wavelength that is not too high and not too low. Why not too high? Because sometimes, especially if it's so close to the near UV, you might get a lot of high background reading. Okay, if you choose, say, for example, 190 nanometer, so you will definitely see quite high background reading. So you want to choose something that is high, but not really too low. Okay, like for example, something like that. 260 might not be your choice of interest. Because why? When you look at the spectra on the right, by changing the wavelength, you can actually change the absorption as well. I know this is very basic for probably most of you guys, but this is something that you need to take into consideration while doing your scouting method. Okay, so one effect is that you will change the absorption peak. As you can see, as you go close to 200, then your absorption spectra is getting higher and higher. But at the same time, while changing the absorption spectra, what might also change is the baseline, the overall baseline of your run. So this might be influenced by the solvent as well. So even if your Analyte is good at, over here is at 210 nanometers, but because there is some issues or incompatibility with the solvent at that particular wavelength, you can actually see it's going down as you increase the concentration of your elution solvent. Okay, so in this case, by running a general, or by roughly running a different wavelength, you can actually see and choose the best wavelength for your run. Okay, especially for something like this, even though it looks clean, neat, and nice, but if you were to open a company that does a lot of analysis, your client might complain because as the gradient increase, there might be some impurities that might come out at the higher concentration, but it is actually hidden because of the increase in the baseline peak. So step 2 for gradient elution is the fine tuning. So new gradient range. So this is in conjunction to this slide. Okay, remember this slide? So when you do a fine tuning for your gradient illusion, example that is shown here is 20 to 60%. What you can get is the previous slide. I should have put an image here. The previous slide shows a rather pure sample, but then when you fine tune, not only you can save time and solvent and whatnot, but you might also be able to identify or give out a better method runs that can identify impurities if it exists underneath the peak. Okay. Additional info for fine tuning and what to look for are such as looking at the pressure, whether the pressure is too high or too low for your run. So there's no correct pressure for Hplc. It all depends based on the equipment itself. So some equipment will run good at 200 psi. Some will consider to be good at more than 10,000 psi, and so on and so forth. So it depends on the machine. So that's why I didn't put any range. I just put it there. Some information that you need to look for during your fine tuning is looking at the pressure to make sure that the pressure is good, and the most important thing is constant. So regardless of regardless of the range of the pressure, as long as it's constant, normally it is okay. Normally, not always, normally. Okay. You need to also consider the elution time. You don't want the elution time to be too long, 1 hour, 2 hours, unless if it's necessary. So you want to reduce the time so that you can inject more sample, you can run more sample, then your company will gain more money per sample. Okay. At the same time, you want to keep your background low as possible. And then, as I showed previously, as you change the wavelength, you can get different baseline or different background reading from noise to signal ratio. So you want something that is more consistent, that is better suited for everything. And then last but not least, you proceed with method validation, which is to rerun the method a few times to ensure similar observation is observed. And as I mentioned, you can either do it in different days, or weeks, or months, or year. Okay. The importance is to run it multiple times, is so that you know that your method can be replicated multiple times using similar setup, similar column, and similar system. Okay, and that is all for the strategy for method development. If you have any question, you can ask now. Otherwise, I will continue with troubleshooting. Any questions? All right. I'm hoping everyone is still here. Okay. All right. So lecture number 5, troubleshooting. So the best troubleshooting strategy is to prevent problems from occurring at the first place. Okay, this is by exercising the best practice in your HPLC operation and by performing periodic preventive maintenance. So if you are a company that does a lot of analysis using HPLC, you need to make sure that your personnel is competent enough to do minimum preventive maintenance. Like for example, if say you do a lot of analysis of a biological sample, proteins, for example, then your HPLC system might use a lot of salts or solvent that contains a lot of salts. And as you know, salts tend to crystallize at one point. Therefore, you might need to train your personnel so that every week or every month, for example, that the person just run molecule water throughout the whole system to dissolve all salts that are present in the system. Okay, this is what I mean by exercising best practices. Other than that, as I mentioned previously, you need to make sure that the sample, the preparation sample, the preparation steps when you prepare your sample are actually adequate, meaning that you know that there is no precipitates in your sample before you inject your HPLC, for example. Or you might want to make sure that your system is fully without a dissolved gas, meaning that your degasser works properly, your pumps work properly so that you get a constant flow. You need to gradually check that, say, for example, if you set 10 mils per minute in your system, that is actually the flow rate that your system actually push out, or the output of the solvent flow is actually 10 mils per minute. Because these things, even though it sounds like, very trivial, but it's actually part of a maintenance to make sure that your system works in a long time. Additionally, you need to make sure that the sample and the column are compatible. So even if your sample might dissolve in the solvent very nicely, it does not, got stuck in any filter, but you need to make sure that the sample or the analyte of interest is also compatible with the column that you want to run. For example, if you are running a C18 lipid, I think I mentioned this same example in my last recorded lecture. So if say the sample that you want to measure is a lipid with a 18 carbon chain, okay, so C18 sample, so it might be an amino acid, or it might be just a lipid that has a long carbon chain. You need to make sure, because the carbon chain is very long, you need to make sure that you don't use a column which also has similar chain length. Because if you do this, even though the lipid itself can dissolve in, say, 50% or 60% of acetonitrile, but once it comes into contact with its like entity, so in this case, C18 with a C18 column, C18 analyte with a C18 column, the forces that holds this two entity together are very strong, and therefore you will at one point block your column. So the system, your HPLC might be working fine, but then now your column is broken. And the cost of column is not as cheap as fixing or replacing a tube in your HPLC. It costs thousands and thousands of ringgit and dollars. Okay, so you want to exercise the best practice so that you can avoid having a problem at all or at the first place. Nonetheless, you might encounter this problem, especially if you are inexperienced, or even if you are experienced personnel. Your HPLC might grow old and cause problems. So you need to know a little bit about HPLC troubleshooting so that you can diagnose and solve the problem at a minimum cost. Okay, I know, it's very easy to just, if you purchase the equipment from, say, Agilent, it will be very easy to just call an Agilent people. Hey buddy, my machine is not working fine, can you just come down and have a look? Yes, that is the easiest way to do, but if you're thinking about the amount of money that you need to spend, then it might not be, if you have a lot of money, then it's fine. But if you don't, then your company will lose a lot of money by just trying to fix something that can be prevented from happening in the first place. Okay, so discussion in this particular lecture or lecture component focuses more on some common problems and their associated symptoms and typical remedial action that you can actually take to try and solve it yourself. If none of this works, then you cannot do anything. Just call someone who can actually do it for you. Okay. So lecture number 5, HPLC troubleshooting. Wait, why is it going back? Wait. All right. So the first thing that you need to do when you encounter a problem is to verify that the problem actually exists. Okay, by repeating the same method or the same experiment for the second time or probably a third time. One example might be if, say, for example, the HPLC is being used by multiple people. So meaning that, this scenario is most likely in a research area whereby, for example, the Department of Chemistry has only a few HPLC machines, but there are a lot of students, there are a lot of researchers that are actually using the system. So the first run normally is normally when a problem will occur. Okay, the problem can be, for example, a leaking. The machine stops due to leaks, or the machine stops due to pressure being too low, or the machine stops because it did not detect anything. Okay, so once you encounter this problem, the first step, in my case, what I normally do is to stop, reboot, and then repeat. Okay, this is what I normally do. So I'll just stop the whole system. I don't do anything. I don't change the solvent. You just stop the whole thing. Whatever you're doing, just stop. You reboot the whole system, meaning that you shut down both the HPLC and the computer. And then you reboot everything again. You turn on everything again. And you repeat the same thing that has caused the problem to occur in the first place. So by doing this, sometimes what might happen is that there might be some signal miscommunication between your HPLC system and your computer. And once that happens, it will just go a beep, 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 and then it stops the whole run and telling you there's an error in this area or that area. So if you actually seen it, or if the error actually comes out for the second time, right after you did all these 3 things, stop, reboot, and repeat, then you know, okay, something is actually went wrong, and you need to therefore investigate. Okay, so what you want to do is you might want to go back to a documented reference application, such as in this case, reference chromatogram. In case if that machine is solely being used by you, okay, you might want to go back to your previous record and see whether the pressure is like this, whether the chromatogram is what expected and whatnot. Or otherwise, if say the machine is being shared with everybody else, normally you will have a book record. So you have a record keeping on the users. So user A might use a normal phase HPLC, user B might use a reverse phase HPLC, and you as a user C, you might want to use a normal phase HPLC. So by changing the solvent system very frequently, you might actually introduce some problems to the system. And by having a record keeping, then now you know, okay, this problem occurs because the person that uses this system before me is using a totally different method, that a totally different system than what I'm using now. So, you know, by knowing this information, there might be some step there might be some step that you can actually do to prevent issues from happening while you are running your first run. Okay, so if the machine is yours solely, especially if you're working in a company, running this reference application with a known good column and sample as well as a mobile phase can often lead to a quick diagnosis. For instance, if you have a pump problem, um, it's indicated if pressure is lower than expected or probably too high than what you normally use. So what you might want to do first is to go back to your initial column, your initial sample, solvents, methods, and so on and so forth, and try and run the system. If you run your reference system and it works fine, then you know there might be something wrong with the method that I developed, or there might be something wrong with the sample that you are currently trying to run. Okay, so this and some examples. Additionally, if a system blockade is indicated in the because the back pressure is higher or too high than normal, then you want to go back and see your records in terms of what are the samples that you have run previously. So you might the sample that you might run previously might contain a little bit of C18 lipid, okay, in a very small quantity, that it does not straight away block your column, but as your sample, as you gradually increase the number of injection, number of analysis, they will build ups of lipids inside your column that finally resulted in a high back pressure. Okay, so record keeping is very important, especially for troubleshooting. So troubleshooting, normally either you go back to your records, or you went and look at the system one by one, to try and find what is the issue with your system. Additionally, the detector might be faulty if peak heights are lower than expected or baseline noise is too excessive. So faulty here does not mean that it's broken 100%. There might be an air bubbles because of the degasser system is broken. Okay, so you know, by knowing all this information, you can actually kind of like know what might be the issue. And if the issue is very simple, like for example, if there's an air bubble in your detector, then you can simply pump it, pump using the normal way to do is, if say you normally run your HPLC at 1 mil per minute, to remove air bubbles, the minimum speed or flow rate that you normally need to use is double the normal rate that you use. Okay, so this is especially true for your HPLC system. For HPLC system, it goes back to type of pump that you use. If you recall on lecture number 2, if I'm not mistaken, some pumps can go between 1 to 5 mils. some can go 1 to 10 mils, some might even go to 15 to 100 mils, and so on and so forth. So it depends on the regular speed of the pump and also the regular speed of your analysis. You might want to change it, but the practice that I normally do is just remove the column and then run the pump at twice the flow rate that I normally do. So if I normally do 1, then I will do 2 mils. If I normally do 5 mils, then during the trying to flashing out the air bubbles, I will do 10 mils per minute. Okay, so what you can also do is isolate the problem by visual inspection of the equipment, especially for leaks. This is in case if the pressure goes too low, or if you are using an auto collector system whereby you ask the machine to collect 5 mils in a Falcon tube, but then once you get the Falcon tube, the volume over there is just 2 or 3 mils, then there might be some leak because you are expecting 5 mils in an FNF tube or in your collection tube, but what you are seeing now is just 2 mils. Okay, so this can be an indicator that there might be some leak. And of course, if the leak is at a particular place on the HPLC, normally the manufacturer put a leak detector in the system, whereby if the leak is excessive, the system will stop it runs altogether. Okay, so why the system stops? Because sometimes if you are doing an analysis, you don't do it between 8 to 5. So sometimes you run the system for 24 hours non-stop. So if there is a leak in the system, say at 12 midnight, so the system will stop pumping, everything will stop, and therefore you can save solvent, you can avoid flooding, and you might avoid some other mishaps, for example, electrocution or fire from short circuits and whatnot. Okay, you can also check for loose cable or tubing connection, meaning that if you look at the system, even if you look at the modules itself, there are at least 6 modules that are interconnecting between one another. So sometimes what you do, if you just focus on the column itself, if you keep on switching between one column to another, there is a very high chance that when you put in the tubing into a new column, the tube was not properly engaged. Therefore, it's a bit loose and leaks might happen. Okay, so by looking at this by visual inspection of each modules, you might be able to identify problem that is caused by either pressure drop or pressure too high, the flow is very low, or even if you saw wet working bench or wet floor, you might be able to find what is the cause of the mishap. Use the built-in diagnostic in each module to locate the problem area. Example, lamp energy reading of the detector, or compression test for the auto sampler. So this is more on the software side. So depending on the software, you might be able to run this. I know we do have some software for Agilent and Shimadzu that can tell you if there's any issue being detected throughout the system. But you might sometimes work with an old system that does not have this kind of feature. So you still need to do a visual inspection. Okay. So other troubleshooting strategies include performing the obvious or easy things first. For example, you might want to replace a check valve if pump pulsation is higher than expected, or you want to troubleshoot one component at a time. because if you just troubleshoot everything at one go, pretty much it does not, well, you will definitely resolve the problem, but it might take a lot of time to actually identify what is the main cause of the problem. You can definitely quickly identify what is the problem, but to identify the cause of the problem, if you run all modules simultaneously, it might be a bit difficult. Okay, it might be time consuming. So normally you want to run one component at a time, and to do this, you normally start from the detector and go backwards until you reach your solvent reservoir. Okay, so you normally want to start with the detector and move backwards. Unless if it's a leak that you can identify straight away, then of course you don't need to check each module, but in case if there's an air bubble, so you know that your system has a degasser. Okay, your HPLC system normally is equipped with a degasser, so there shouldn't be any bubbling issue. But then your detector says otherwise, and by running the pump at a higher speed, you can remove the bubble. But that is not um, by just doing that, you are not solving the primary issue, which is how the bubble actually forms in the first place. So you might want to, because you don't know where the bubble comes from, and if you cannot see it, then definitely you will need to search, or by looking at each module one by one slowly. Okay, by doing this, you might want to check the tubing, the connection between each module, because sometimes because it is loose, so you can introduce air bubbles from there. Bubbles might be very small, but over time you can actually see the bubbles getting bigger and bigger. Okay, so that's what I normally do. So troubleshoot one component at a time. You might also, if your company has extra modules, swap suspecting module with a known good ones. So if you have two machines, for example, and one machine is currently used, or one machine is not used, and the machine that you want to use actually has a problem, so you might want to try and swap the module and see if the problem actually goes away. If it does, then then you can suspect that the module is actually, there's some issue with the module, regardless of what the issues are, but you know that the module is the primary culprit in your problem. Okay, and of course you can always consult service expert or manufacturer to just come to your office or your lab and fix it for you. That's the easiest way to do. You can save a lot of time, but you cannot save a lot of money, unfortunately. Okay, so do the simplest replacement yourself, but leave the more elaborate operation to your service specialist. So say for example, if you just need to change a tube, then might as well just change it yourself, because it's easy enough, especially if you have all the tools, and the tools is not as expensive. It might be more expensive to actually call a service provider than to actually fix it yourself. All right, when you're talking about reference chromatogram, using a common or known chemical and methods, this is what I mean. Okay, so say for example, this is your first run. Your first run, once you optimize it, when you validate it, the first run is very clean and it looks like this. Okay, if you can see, the detection is okay, not too small and not too big. The background is very nice. Over here, you don't even see the injection peak, which is fine, excellent. Even though you normally see it, but this is still okay. And from this information, you can know that the plate number is about 3,150. The initial pressure for the whole system, including column and whatnot, is about 2,500 psi. You know the retention time of this particular compound is at 2.27, and tailing factor is 1.3. So in the future, if you run into a problem, you might want to go back to your reference and do a comparison between your current data and the data that you've run initially. So because you know that this is the best, so if say the plate number now becomes 2000 or 1500, then you know that your system is actually running a maximum at 50% of what is capable for previously. So you might want to do some servicing, or perhaps changing some components of your modules of your HPLC, so that you can reuse it once it is fixed. Okay, so common HPLC problems are caused by component malfunction and faulty preparation of the mobile phase or sample preparation. Problem can be categorized into several areas, including, so this is the 3 highlighted areas that I've chosen. So first is pressure problem, second one baseline problem, and number 3 peak problem. So baseline problem and peak problem are related in the sense that both of them involve the chromatogram, but as you will see next, I will give out a more specific examples in each category. Okay, so for the first category, pressure problem, so say if the pressure is too high, so what might be the issue? So it might be caused by partial blockage of the system component, such as filter, the guard column, the column itself, the tubing, injector, or the detector. Okay, and the most common ones that I've seen based on my experience of more than, now it's 2021, so more than 10 years of using HPLC, the most common problem when pressure is too high comes from filter and guard column. So that's the most common ones. So meaning that the filter can be either the inline filter. I'm not sure, probably I did not touch about this, but anyhow, so it can be an inline filter. So this definitely, anything that is not in your lecture notes, I would ask you to actually memorize. This is just a basic additional information for those who are planning to work with HPLC in the future. So your inline filter might be blocked, or you have this small metal grid filter that is filter that is normally located around your pumps. Okay, so pumps and then some other modules which I can't remember where, but it's definitely in your pumps. Okay, I definitely remember changing my filter in the pump itself. So you know, when you use samples, and especially if the machine have been running for years and years, this problem, if it exists, it's not a big of deal. So what you do is either you just change the filter, or change the guard column, or you can even clean the guard column. Guard column can be simply cleaned by using a solvent that can dissolve most of the sample that you have used or you have analyzed previously. So say, for example, in my case, my sample mostly comes from a synthetic peptide source. So I know that my peptide definitely dissolve 100% in IPA, isopropyl alcohol. So if I were to clean my guard column, what I would do is I would just take out the guard column from the guard column housing, put it in an IPA solvent, and then I'll just tonicate it for about 5 to 10 minutes. And then after that, I will just rewash it and then do it multiple times. I mean, the sonication process while changing the IPA. And then for my final wash, I will normally wash it back with either acetonitrile or water, because these acetonitrile and water are the main two solvents that I use for my peptide analysis. So, just simply washing sometimes helps to lower the back pressure. But of course, if your gut column is the main culprit, then you should know that it won't take long for the gut column to be clogged again. Therefore, if you do have extra money, you might want to replace it. Okay, something that you don't want to happen is by knowing that the back pressure comes from your column. Okay, if this happens, you might want to cry because column is expensive. Unless if you are working in a company that sells column for a living, then you can probably be happy. But otherwise, if your column is blocked, it will definitely cause a lot of problems, because now not only the column is blocked, but you might not be able to run your HPLC if you do not have an extra column. Okay, so the first thing that you do is you want to isolate the source of the pressure, the high pressure. Okay, as I mentioned, you normally start off near the detector and then you move backwards, meaning that say for example, if you run your pump at say 10 mils per minute, and then the back pressure that was given is 5,000 psi, what you might want to do is, first off, you detach the last tubing connecting the column to the detector. Okay. So what you might want to do is, first off, just take out that. So you want to disengage the last tubing going from the column to detector. Just open that one, and then put in a beaker, and then run your system at 10 mils per minute. If, say, your pressure goes down to about, say, 4,950 psi, then you can say, oh, there might be some impurities in the detector, but this is not the main culprit, especially if your reference run is 2,500. Okay, of course, this is a theoretical example. I do not have a record of my issues previously, so this is just a theoretical. So once you know that when you disengage your tubing towards the detector, the pressure only goes down just a little bit. What you do next is you move back to the column section. So now what you do is, column is attached to a mixer or probably an oven, based on, of course, we have auto collector over here, but I'll just cancel out auto collector. Just imagine that this system has no auto collector. Okay, so you have an oven. Normally, oven is just a storing. So yes, it goes back to the pump or mixture. Okay, so you might want to open this particular tab, put it in a beaker, and then again run the pump at 10 mils per minute, and see if your pressure is going down. If it goes down to less than 2,500, so say if it goes down to say 200 psi, even though it's very low, but you now know that the issue comes from the column. Okay, so why did I say that normally the pressure is 2,500, but then once you remove the column, 200 is normal? Well, this is because at a normal loading, okay, with column attached, without sample, the system might run at 2,500 psi. So if you remove the column, it will not jump from 5,000 to 2,500. It will jump from 5,000 to 200, because currently there's no column, and because the column is clogged, then definitely the pressure will go very, very low. You might not be surprised that the pressure can go down from 5,000 to about 10 psi. Okay, this happens, or even 1 or 2 psi, especially because if there's nothing blocking the flow rate, then the psi normally will be very, very low. For instance, if higher than expected pressure is experienced after disconnecting the column, the blockage is occurring upstream in the injector pump, as I mentioned. If the pressure is still high after disconnecting tubing to the injector, the problem lies in the pump. The most likely location of blockage is the column that is packed with small particles. Okay, so that's what I mean. So most common is column, but if you have a column guard, then it will be a column guard. And if you have an inlet filter, then normally the problem will goes here. So that's the level. Normally, the inlet filter will be blocked first, and then your column guard, and then your column. Okay, high column back pressure can be remediated by back flushing or replacing the inlet frit of the column. Okay, so if you recall, inlet frit is the kind of like a filter that holds or that covers your silica inside your column from getting out. Okay, so you can either replace this or that, but again, you might not be able to replace it might not be as easy to replace the inlet frit because the column is normally developed so that a normal user cannot reopen it. Okay, but of course you can open it if you want, but normally you can't. All right, a high pressure problem should be investigated early before total blockage occur. So if originally it's 2,500 psi, and then on the day of your run it suddenly jumps to 4,000 psi, even though the system it still runs perfectly, you might want to stop what you are doing and then investigate before it goes to 5,000 and thus blocking your system from running altogether. All right. Okay, I've already drawn, so I can skip that one. So what happens if the pressure is too low? So lower than expected system pressure is caused by normally leaks at piston seals, column connections, injector, or pump malfunction. Okay, which you will definitely see it, and by looking at if there's any flow at all. All right, so there might also be an air bubbles in the pump head, or vapor lock, which is very, very unlikely, but can happen. Faulty check valve or a broken piston. So normally, if a broken piston, then you will hear like a very loud noise. Also in liquid solvent supply, so empty solvent reservoir, plug solvent sinker, bent solvent lines, and wrong solvent mixture. So a lot of things can happen if the pressure is too low. Problem diagnosis can be made by visual inspection for leaks or by monitoring a pressure reading of the pump in the system or software. Okay. So far, all the three main brands that I work with, Hplc, you work on. Okay, so all the three main systems that I worked on, Agilent, Shimadzu, and Waters, all of them has a pressure values in the software. So by just looking at the software, you know whether the pressure is too high or too low. Right. So what might also happen is that the pressure is cycling up and down, meaning that it doesn't go down and stays down, it doesn't go high and stays high, keeps on doing that, like a sinusoidal curve. So pressure cycling is normally caused by air bubbles in check valve, okay, check valve in the pump, remediated by degassing the solvent, malfunctioning of check valve or pulse dampener, or partial system blockage. Additionally, yep, for pressure, if it goes up and down, then definitely there's an air bubble somewhere in the system that keeps on going up and down. Normally is in the pump, because the pump is where the solvent capacity is the highest. As you go outside of the pump into the auto injector or solvent mixture, or even the column and detector, the solvent reservoir or the void volume in these other modules are very, very small. So even if there's any trapped air bubbles at these other places, normally by just running your solvent flow at the normal rate, you normally will be able to excrete out all the bubbles. Malfunctioning check valve is typically the result of trapped air bubbles or contamination of the ball and seat mechanism, causing incomplete closure. Okay, it usually manifests itself by significantly increased pressure fluctuation that are synchronous to the pump stroke. An air bubble can be removed by degassing all solvent or by purging the pump with methanol or isopropyl alcohol that wets the check valve more effectively. Malfunction check valve should be dismantled and cleaned or replaced by a new unit. Okay, check valve, if you look at this pump, so that is actually the pump, one of the pump component. If you open this, in this system, it's a binary pump. There's only like one pump, so you can just open it and clean the check valve. All right, so this is an example of a pressure cycling going up and down. As you can see here, for a normal run, normally it will just go flat. Okay, but if it's cycling, it goes up very, very high during the piston stroke, and then during the dampening effect, it will go something like this. So you can see that it's still going up and down, and then pump stroke again, and then dampener, pump stroke again, dampener. Okay, so by looking at the pressure, you can actually know if there is any issue that is caused by particularly the pump. All right, so some other problems that you might encounter that is related to pressure problem is normal pressure fluctuation less than 2% of a nominal pressure. Okay, as even if you see like that, so it's not flat, so normally it's very flat. Something like this is an indicator that in the near future something is going to happen that stops you from doing whatever you are doing. Okay, pressure cycling caused by bad check valve or an air bubbles in the pump head can also be something like this. So this one is a change in the pressure. So the pulsation is synchronized with pump stroke. Example, if there's 10 cycles per minute at 1 mil per minute for pump with piston volume of 100 mil. So if you see a regular interval like this, then it's a good indicator that the pump is actually the main issue culprit. So second one, the second category, which is a baseline problem from the chromatogram. So manifestation of inconsistent baseline can be in one of these examples. It can be a noisy baseline, a cyclic baseline, a synchronous noise, spikes, asynchronous noise, no peaks, drift, positive or negative peak, while running just a blank sample or a blank run. So meaning that you are running an isocratic flow, you did not inject any sample, but your baseline is like this. So one issue that happened to me last time, which is very funny, was that the module was actually disconnected from the whole system. For whatever reason, it's a very unfortunate event, because at that time I've already injected my samples and whatnot, and then later on I noticed that the baseline did not change at all. So while doing some inspection and whatnot, doing my reboot, I noticed that, because sometimes when, so the funny thing about especially Agilent HPLC is that, if initially at time zero, um, all modules are connected properly with the software, if there is any issue happens, due to loss of connection and whatnot, sometimes the system will not register there is an issue. Okay, so that is what happened to me, especially because the HPLC system that I've used at that particular time was, rather old. It's an old system, so the software was a bit outdated. Therefore, it did not tell me that one of the modules are actually disconnecting because the cable was broken. So by doing a lot of analysis, I actually waste a lot of time trying to figure out what happened, and then I finally, um, just simply switching the cable and it works. So sometimes something like that can happen. It's very unexpected, but it might happen. Okay, so moving back to the baseline problem. So some problems and their reasons are, if you have some noise, like this or any other noise, as I've shown in the previous slide, you might actually have an aging detector source. So detector source meaning that, if you are using a UV vis, so your lamp, the lamp source might be broken, or it's already too old to be able to give you a consistent light source. Okay, if say, number two, if you see um, a flow off, a sudden flow off, as shown in the right image here. So initially you can see the pressure is going up and down, and then suddenly you get a total flat. Even if you zoom in, you will see a flat. So you know that there might be some issue with pump pulsation, and this can very easily be investigated by just putting your ear very close to the pump. Because for HPLC system, regardless of which brand, you normally can hear like a very subtle noise about, when the pump is actually working. So if the flow is suddenly goes flat, and by inspecting the pump you can't hear anything, then you know that either the pump is broken, or, as in my case, one of the cables is broken and whatnot. Okay, spiking in a chromatogram can be as a result of an air bubble in a flow cell. So the flow cell is inside the detector. So what might happen is, normally you have a flow cell like that. Okay, so and you have your light source coming in. So I'll just do like that. Okay, you have your light source and your solvent is moving towards that direction. Okay, if you have an air bubble somewhere here, so when the solvent pumps in, the air bubbles might move um, in front of the light source, and therefore give you some reading. And then once, because regardless of how, depending on what type of pump that you have for your HPLC, it might normally be a sinusoidal pump, even though you have a dampener and whatnot, but you might still see the pressure going up and down. So while this happens, if a big bubble is actually present in your system, what might happen is that the bubbles is just simply moving up and down, passing through the light source. Therefore, you see this, spiking, random spiking happening any time of the day. Additionally, if you do have a very high background, it might be, especially if you are using a UV-based detector, it might be due to the solvent wavelength cutoff or solvent contamination. So solvent cutoff is the graph that I've shown you initially, whereby the peak cutoff is around 200 nanometer. If that happens, then you know that your solvent is not really compatible, thus give like a quite high baseline reading, which is, you know, it might be okay in certain case, especially if you do know that your analyte is at higher concentration, so it might be fine. But if the analyte that you are measuring is very minute, then having a high solvent UV cutoff is bad for your analysis. Short-term detector noise can be estimated by using an expanded scale and measuring the peak-to-peak signal fluctuation of the baseline. The noise of a modern UV detector should be close to the published specification, or about 0.1 micro AU. Noise baseline is typically caused by low energy of aging UV lamp, which should be replaced. Okay, this is just an example of a noisy baseline. An alternative, detector noise can also be caused by large air bubbles trapped in the flow cell, or pressure fluctuation caused by a small leak in the flow cell. So why flow cell? Because flow cells affects chromatogram, which is the baseline. Okay? A noisy baseline is of a reflective index detector, can be caused by inadequate mobile phase degassing or temperature thermostating. However, low light energy can also be caused by a contaminated detector flow cell or high UV absorption of the mobile phase. Okay, so these are some other examples. All right, synchronous or asynchronous noise. So cyclical baseline noise in synchronous or pump stroke is typically pump related. So this one is as what we've touched a little bit. It might be some issue with the pump. Well, there definitely is some issue with the pump normally. Okay, but again, because we are talking about the detector, so it might be from the pump, it might not be from the pump, because if there's an air leak from somewhere else, or if the degasser system is now broken, then you will get accumulation of air bubbles, and therefore you can get a baseline problem as shown in this picture here. One definitive test for pump related noise is to check the noise is eliminated after the pump is turned off. So either the pump is off straight away from the start and you cannot hear the noise, or it might be that initially there's a noise, and then when you stop the pump, then either the issue goes away or you eliminated the issue that you observed from the detector. So you know the issue now is related to the pump. All right, desynchronous noise can be caused by pump malfunction, small air bubbles in pump head, check valve problem, broken plunger or piston, or faulty pulse dampener. Inadequate mixing of mobile phase is also a possible cause of solvent bending at pump if solvent blending at pump is used. Okay, or synchronous detector noise can be caused by electrical sources, which is such as ground loop problems, power voltage fluctuation, or electrical shielding problems, and so on and so forth. So this is more difficult to diagnose and remedy. And normally, if this actually happens, and once you have eliminated out all the other problems, you will definitely just call a technician from the manufacturer to actually come and look at your system. Asynchronous noise, on the other hand, is likely caused by the detector, such as leaks, loose detection connections, or can also be electrical problem. All right. Baseline drift. baseline drift is a UV absorption. Okay, this is a picture after this. Baseline drift in a UV absorbance detector often reflects a change in energy output of the UV lamp with time. A specification of about 1 or 10 milli-AU per hour is typical. Baseline shift associated with gradient analysis are also quite normal. So this is the one that I mentioned in the previous slides. They are caused by the difference absorbance and or reflective index of the initial and the final mobile phase. So this is especially true if, say, for example, this is just based on previous slide. If you are running 0% acetonitrile and you are finishing at 100% acetonitrile, you definitely know that at 0% acetonitrile, there is 100% of one type of solvent. Typically, for a reverse phase Hplc, is water or a ultra pure water. So similarly, at 100% acetonitrile, there's 0% of ultra pure water. So just looking at these two molecules, you do know that the absorptions are totally different, okay? Because they are different molecules. It has a different vibrational bands. It absorbs energy at a different wavelength, and so on and so forth. So there will definitely be a solvent baseline drift. So how does a drift looks like? So this, oops, what have I done? So this is how a drift looks like, okay? So without drift, normally the baseline stays at close to 0. With a drift, you can see that initially the baseline is close to 0, but after your run has finishes, that one is about 0.1. Okay, so this is what we call as a baseline drift. A small drift is typically okay, but once your drift becomes too big, say for example, if your drift is about close to 1 AU, then something is wrong with maybe your detector or your system altogether. Okay, this gradient shift can be minimized by balancing the absorbance of the two mobile phases and or by using a flow cell designed to minimize the effect of reflective index changes. So normally for this one, you can always use a quartz type detector module, which is more expensive, but it reduces the effect of baseline shift. And balancing the absorbance of these two, what it means is that if say you have acetonitrile having that kind of UV spectra, while water you have something like that. So instead you might want to use a wavelength somewhere in the middle, not too low and not too high. Okay. Non-specific drift can be caused by strongly retained peak slowly bleeding off a contaminated column. So contaminated column or an old column or a column that is being degraded. Okay, so it's a very normal thing to happen. This problem can be remediated by purging the column with a strong solvent until the baseline is stable. So, you know, either buy a new solvent which costs money, or you pumped it with a strong solvent that will also cost money. So either or, it will cost money to try and revive a waning off or damaged column. Drift can also be caused by temperature fluctuation or small leak in flow cell. So flow cell, especially for UV, because it's light, there's an energy, so there's tend to be some heat ups, heating element over there. So that is what it means by temperature fluctuation. Alternatively, if you are using an oven for your whole system, if your oven is broken, then it might lead to a baseline drift. All right, spike problems. So it is normally caused by air bubbles bubbling out or gassing in the detector flow cell. So this is what I mentioned previously. They can be eliminated by mobile phase degassing or purging. Spikes can also be caused by poor signal wire connection or loose or damaged data wiring and malfunction of the detector or the data system. So this is what happened to me a long time ago. All right, so number 3, peak problems, chromatogram. So very common peak problems are poor resolution, broad peaks, split peaks, tailing or fronting peaks, extra peaks, in most often caused by a column and its interaction with the mobile phase and the sample. So no peak in a chromatogram, injector not making an injection, a pump not delivering flow, big leaks, that detector, a miswired system, wrong mobile phase, and so on and so forth. So how do you diagnose this? The best procedure to diagnose is to go back to the reference test condition. So this is the first run for the whole system. Okay, either it's a brand new system or if even if it's an old system but you just recently being tasked to use the system, so you keep it as a reference and you can always go back to use that in case to use the information to diagnose if such problem exists. If the reference condition can be duplicated successfully, okay, so if it's successful, therefore inferring that the system is functioning properly, then the troubleshooting effort can be directed to specific application condition such as the column, mobile phases, sample preparation, and so on and so forth. Okay, for example, weaker and equal. Oh, I think this image is a bit off. I think I accidentally cut off the y-axis. Okay, so this one means that equal in peak height. All right, the ones on the right hand side, broad or split peak. This one is not related at all, unfortunately, but this one, broad and split peaks, is something like this. Sample solvent strength relative to eluent. You might get some broad peak like this or a split peak. And if you have run this sample previously, you can go back to your reference data and see if you actually saw similar instances during your first run. So broad and split peaks, abnormally broad peaks or split peaks are indication of degraded column performance caused by sample contamination, partially blocked inlet feed, and column voiding. So this is an example where initially that is your reference, and this is now, or is there after failure. So if initially all the peaks look symmetry enough, so peaks are symmetry, there are no tailing or overlapping peaks, so you do know that something is wrong with the column, and especially because there's a huge drift between some of your peak, then you know that okay, this is as a result of the column. Otherwise, you might not, if the drift is very minor, then you might want to investigate something else, like such as your solvent concentration and whatnot. Okay, so if the column is the main culprit, so you can easily fix it by doing a back flushing. So what it means is that if you have used an Hplc, a column has its own designated inlet and outlet. Okay, so you normally don't keep on switching in and out. And what backflashing means is that you flow it, you now switch the flow, but at the same time the flow rate is being halved. Okay, so this is a common technique to do a back flushing. Refilling the column inlet with packing and more often replacing the column, okay, because this one is very easy. So other consideration that you might want to do if you do see a broad or a split peak is so peak shape can be caused by injecting sample dissolved in solvents stronger than mobile phase. So this is as what I mentioned like the very beginning of the lecture, whereby sometimes you dissolve the sample in methanol, but then your system, when you run it, you use acetonitrile and water. So you might see this to happen. Okay, if possible, the solvent for dissolving the sample should be of a weaker strength than a mobile phase. If strong solvent must be used, the volume should be kept at small, especially in other cases like if you have issues with sample dissolving in isonitrate or water, you might want to use, you might try and use DMSO, dimethyl sulfoxide, which is a very strong solvating agent. So if you do use something like that, then definitely it will affect a lot of your data. Okay, if a strong solvent must be used, the volume should be kept at minimum or small to prevent peak broadening or peak splitting of the early eluting peaks. If you use too much, what might also happen is that the solvent will carry the analyte of interest and it will elute very early or at the very beginning of the peak run. So peak splitting can also result when the sample pH is different from the pH of the mobile phase. Okay, so normally when you prepare your sample along the process and whatnot, you want to keep everything as close as possible. You don't want to keep on changing pH, whereby when you prepare your sample, you don't want to prepare in a buffer solution, and then suddenly when you want to run it, you run it in an acidic solution. Okay, how many slides do I have left? So I still have 7 slides. Should I continue? I'll probably just take a break for a while. I need to drink. So we'll come back at about, I'll just finish it. I'll just finish it very quickly. Okay. Fronting and tailing peaks. So fronting peak means that the peak, the tailing is at the very beginning of the peak. Tailing means it's going up and then tailing out once it's eluting out. Okay, so it's normally caused by column overloading, sample amount exceeding the sample capacity of the column, resulting in some of the analyte eluting ahead of the main analyte band. So to solve this, if you do see something like this happen, to solve it, you just inject less sample. Tailing peaks, on the other hand, is caused by secondary interaction of the analyte band with a stationary phase or basic compounds. Peak tailing of a basic analyte can be reduced by adding amine modifier, for example, 0.1 trimethylamine to the mobile phase, or by replacing the column with lower selenophilic activity. Asymmetric peak shape can also be caused by chemical reaction or isomerization of the analyte during chromatography. So these are some problems that you might encounter in the future, and if this happens, then you know that you know you need to investigate and do something about it. Otherwise, the issue might persist, or it might cause more issue in the future. Right. So this is what peak tailing is over this one, and this one is fronting. Okay, fronting. Right. So negative and positive peak. Negative peak or a dip in the chromatogram are commonly near the solvent front. They are caused by refractive index changes or by sample solvent with less absorbance than the mobile phase. These baseline perturbations are usually ignored by starting data integration after the solvent front. So this is what I mean by at the very beginning of this is the one that where I call the sample injection peak. Okay, so it's a negative and a positive peak, and it's normally caused by it says here sample solvent with less absorbance than the mobile phase. So solvent, meaning that when you prepare your sample, you actually dissolve it in a solvent, and that solvent has less absorbance than your mobile phase that you are running. Therefore, you will see this positive and negative peak to occur. However, if all peaks are negative, it might be an indicator of a wrong polarity of the detector wire connection. Okay, especially if you are using a PDA system where it's a photodiode array. So a diode needs to have a certain polarity, plus and minus. If you switch it, it will still work, but it will give you the opposite reading, which is what is happens here. Okay. Ghosts and extra peaks. Ghost peaks are associated with blank gradient, meaning that when you are running your blank, you actually see a peak coming out. These are usually caused by a trace contaminant in the weaker mobile phase and can be minimized by using a purified reagent or by exercising stringent mobile phase preparation precaution. You might also see a mobile phase from column. So I didn't put it here, but it might also come from column, whereby when you do run number one, for example, you actually had something that is stuck to the column at a very, very long time. So you need to actually wash it multiple times to actually clear out this ghost peak. Unexpected extra peak, particularly those which are unusually broad, are typically caused by lead eluting peak from prior injection. Okay, so this can also be the cause of a ghost peak. Some of these peaks can be so broad that they are often mistaken for baseline drift. So what do I mean by that? Is like here. So this one is a ghost peak, whereby you can actually see it's a blank run, but you see peaks coming out. Okay, so that what is mean by this is what it means by ghost peaks. Additionally, an extra peak is when you see an extra additional peak coming out following a second injection. So if you are doing an analysis of same sample twice, and then suddenly on the second run you see a new peak coming out, then that peak is an extra peak. Then you need to investigate and probably go back to your method development to make sure that your method actually able to clear out all contaminants from the column so that your run will be repetitive again. All right, I think that's it. Thank you for everything. If you do have any questions that you want to ask, then you still have about half an hour to do so. Either you do it now or you can just always talk in the WhatsApp group. But I think that is all from me. Thank you for being here for the past few weeks. And even though we were not able to, come meet face to face and doing all these activities, but at least you gained some knowledge from me, and I would say good luck for your exam in the 5th of February. Okay, so don't forget to submit your assignment, because I will start marking it next week. If you have not submitted your assignment, then there might be some issue, because I need to give out the grades for continuous assessment, meaning that your assignment plus your quiz, I need to give out the grade by next week. So because we had a lot of holidays and whatnot, so I'm hoping that you will be able to submit your assignment by today, so I can start marking and process all the marks and give you guys the grades that you deserve based on your work by next week. Okay, and hopefully by knowing your grade, you can estimate how much effort you need to put in for your final exam. Okay, so again, your final exam is only for 1 hour. there are three. Wait, was it three? I can't remember. I think it was 3 or 4 main questions. Of course, there are sub questions. It's supposed to be a closed book, but since everybody's taking the exam at home, I cannot. Even though I'm gonna say it now, it should be a closed book. But if you do look at your books, I have no idea. What I can say is that if I were able to detect that the sentence comes from any websites or lecture notes, then you'll be in trouble. Okay. Otherwise, if you do it on your own, it will be okay. Okay. Any questions before we end our class for today, or for the whole semester, not just for today? If not, thank you, and I will see you guys during the exam day. Thank you.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.